Hey everyone, I'm Wanderson from Houdini VFX, and welcome to this exciting new tutorial. We are going to break down a powerful disintegration effect using Houdini. Whether you're just starting out or already diving deep into FX, this project is packed with tips, techniques, and that cinematic vibe we all love. In this course, I will show how I created this epic arc disintegration shot to fracturing, dissolving, and adding those final effects touches in Houdini. Let's get started. Let's create our first node, create a geometry, rename this to arc, disintegrate. Let's go inside the node and import our geometry. Let's pick up our geometry here. Let's disable convert units to scale up to the correct size in the world. This geometry I created in Zbrush. If you want to know how I created this arc model in Zbrush, you can watch the video in the description. Let's match size, align it to the grid in Y. Let's scale to fit to 1 unit box. Convert this geometry. Because this geometry is already packed, we need to unpack this geometry and delete some attributes. Let's delete some attributes here. The only attribute that we need in this geometry right now is naming, primitive names. This is important to organize our fracture and organizing the geometry in the shaders. Delete non-selected and preserve the name. And you need to use a vex expression here in primitives to preserve this name, because when you fracture this geometry using cluster, instead of using Voronoi here, Voronoi is a kind of slow. We are using cluster to fracture in this geometry. We need to preserve these name attributes to use later in the simulation. Let's rename this to vex, pick up a name. Let's colorize this to purple and create an attribute here. S at old name equals S at name. We are creating the same attribute with a different name because we need to restore this attribute to the original name later in the processor. Let's clean out this geometry. When you apply the clean here, there's a problem because there's a lot of vertex. This geometry is too dense. And you need to clean, but we need to reduce the degeneracy colors. Perfect. Now we need to apply a rest position, because the first step here is to make the fracture. Use a cluster. And define here like 100 clusters. If you want to know a tip, for example, if you want to use Voronoi here, it's possible, but this node Voronoi is like a much more slower version of this cluster. You can use Voronoi, but take a lot of time processing the geometry fracture. I prefer to use clusters. To see the cluster information, you can enable this attribute here, cluster. You can see the fracture, the fragments. If you observe here, the fracture is to a line. We need to break up this line. To do that, you need to apply a noise before you enter the geometry in this cluster node. For that, use noise, attribute noise, change this to P, to position. This noise is not good. Let's adjust the amplitude to 0.2. Element size to 0.2 as well. Perfect. Okay. Now the cluster information should be more integrated. There's a lot of more breakups between the edges of the fragments. If you want to see the result here of the fragment, just use another rest position to restore the initial position of each vertex. And you apply here, switch here to extract rest. And you can see, when apply this, there's a lot more breakups information in the lines. Instead of linear, we have a lot of variation here in the boundaries. That's cool. But this rest node will be disabled here. We don't need the rest here. We need to apply some operations before going to the geometry to the rest position. Let's create an attribute promote. Because you can see here, there's a cluster attribute which identifies each point for the cluster. We need to promote this cluster attribute to primitive. Use attribute promote, enable here. Change to cluster. Point to primitive. Promotion method to maximum. And the cluster attribute appears here in primitive tab. Let's use a node primitive split to separate each primitive, because you can see the separation, but just in colors. This is still a connected geometry. If you want to see that, you can apply an explode view just to check. There is no explosion here in the piece, just in the parts. Here's the teeth. Here's, I think, the eyes, the rings, but not in the fragments. To apply the separation of the fragments, you need to use this primitive split here. And change the attribute to cluster. Change the tolerance like 0.3. And then you can see now the explode view. Let's create a for each to create more piece inside each colored piece here. For that, we use for each connected piece. Let's just see the single version of that. This piece here. And you need right now fragment again this piece to smaller fragments. For that, we create another cluster. Around the 40 pieces. That's iterations 1. And change the seed like 40, 50. Let's see the new cluster format by create a hemp from attribute, change this to cluster, 0 to 100. First, let's disable the cluster visibility here. And you can see the separation of the fragments. Now you need to apply another attribute promote. to promote again. Cluster, points from primitive, and maximum. And use another primitive split. Change this again to cluster and change the tolerance to 0.3. Let's see the information. Let's apply exploded view. Let's delete some attributes here that we don't need. Let's delete the color, cluster, class, and cluster. We don't need these attributes anymore. Let's delete this node. Let's use assemble geometry. Just to restore these attributes. This assembly node is just to restore this information here for it to pack the primitive. But right now we need to visualize the entire head, apply a rest position. Actually, we need to restore this rest position here. Extract. The pieces are going to the original place, original position, and we need to delete another attribute here to clean up the geometry. We need to delete everything except the rest, and name and old name. These two attributes we need to keep. To avoid the processing of the fragmentation of this head again, when you're going to start the simulation, just create a file cache here. This will be the first cache to save the memory and space and processing. Let's change the name to cache cluster shapes. We don't need the time caching. In the advanced tab, we disable this hardened base name on save and change it here to parent plus node name. And let's make the cache. Let's save the cache. Right now, we can see here the geometry is too dense, but we don't have yet the separation of this piece. Let's use the explode view to check if the fragments are working. Perfect. All the fragments are working. You can see here the separation. This technique of fragments using cluster is very good instead of using the legacy Voronoi technique. Right now, we are going to apply a vellum simulation here to spreading out the simulation. But for this, we cannot use this geometry because we have a lot of polygons. We need a low resolution version of this geometry. For this, we need to use a remesh. Before applying connect this to the remesh, let's disable here to manual to avoid the processing and change the target size like 0.1. Now we can enable this manual to auto update and see the remeshing of each geometry. Instead of using around the 700,000 points, right now we are going to use 300,000 points in the simulation. Let's organize these nodes, delete some nodes we don't need here. Delete this node, delete the explode. Let's organize this. We don't need this node here. We can disable this node. Organize this. Let's create a vellum cloth, vellum configure cloth. Disable here the manual. Connect the remesh to the vellum cloth. We don't need to change anything here. Create a valence solver. Connect the valence solver to the valence cloth. Change the time scale because we are going to use a lower version of the simulation. Let's change the time scale to half. Enable the ground position. And disable the gravity. We don't need gravity in the simulation. Let's create another cache here, file cache, just to interpret how the simulation are going to behave in the first time. Change the name to cache peeling. Change the base name to parent plus node name. In the advanced tab, we disable harden base name on save and enable initialize simulation ops. Let's cache and see what has happened in the first version. This is the first simulation of these fragments. The fragments are just floating and is not activating like the mask. We need to create a mask to activate each fragment to start simulation at its respective time. To do that, we need to create a mask. And before creating a mask, this cache took around 4 minutes to take. We don't need to cache the whole geometry again. For that, we can clip this geometry, and in the phase of the experimentation, we just need to clip this to see the part of the geometry in simulation. We don't need to see all the simulation in the work in progress. For this, before the remesh here, we can clip this geometry just to preview. Create a switch here, preview, and here clip the geometry in the X position, and clip again in the Z position. We just needed to see 1/4 of the geometry in the simulation before the final simulation. Can enable here, switch preview. And let's create a mask right now. For this the activation mask, we need to store the rest position. Here in the valence cloth. Let's rename this to store rest. Create an attribute noise to change the position of the vertex, the points. Let's change it here to P. Amplitude 0.3. And element size 0.2. Let's create a group. Rename this to group inside. Change the group name here to $OS. Disable the base group and enable the keep in boundary regions. Let's enable the preview here just to see if the whole geometry is inside the selection, the group box. Change this to 0. Enable initialize to input bounds and change this here to sphere, bound sphere. Let's increase here in the X, the Y, and the Z. Let's make an keyframe here in the size. Left click keyframe, set keyframe, left click keyframe, set keyframe. This is the first keyframe. Let's change here in the global animation options, the FPS to 30, apply FPS, and the frames to 240. Apply. Let's apply this keyframe again here. Left click, keyframe, set keyframe. Left click, keyframe, set keyframe. The animation of the first frame, the bounding box should be outside of the selection. Left click, set keyframe, set keyframe. And the animation should be like this. Let's go back to the rest position here, extract the rest. Extract the rest. Let's see the color information of this, the group inside the group. Group inside, let's change it to red and see what is happening. You can see a masking forming here. The detail of the mask is good. It's not linear. You have the fractal here. This activation, the color activation here is good. For activating the geometry by this color, we need to create an attribute. Attribute create. Change this attribute to activate. And change the group here from attribute create to group inside. Let's change here in the group inside to group type to points. And create a checkpoint here. Ref activate pieces. How to use that in Valon simulation to activate only the piece, the red piece in the simulation. We need to go inside the Valon solver. Let's disable this node, this option here to manual to avoid the rethinking of the simulation. Here, inside the Valon node, we need to first create a poppy wrangle. Poppy wrangle nodes, just to apply the simulation in activated pieces. For that, we need to use a VEX code, VEX script. The VEX script should be like this. Let's check the name of the active attribute. Okay, let's go inside. In the inputs, we change here to second input to SOP. The SOP information here should be this node here. Ref activate piece. We can just copy, Ctrl+C, go inside the Valon solver, Ctrl+V to pass the path. And the code information here, we just write this script. E.activate piece equal point 1 activate. This point function in VEX will grab the point information from that input, from that input 2, which represents this node here, the color information and the activate attribute. Activate by dot at ptn and create a mask from that. We store the mask from the outside node. And create a condition here. If e at activate piece at mass equals mass, else at mass equals 0. The script here is a logic for that. We check the activate attribute from each piece. The active piece should be red. If the piece is activate, we can enable the mass and the piece is starting flowing in the simulation. If the piece is not red, is not activate, the mass should be 0. In the value simulation, if the mass is 0, there is no simulation. It's like I stacked the geometry inside the simulation. See what happens and make this cache. Let's change it here to preview. We don't need to see the entire geometry, just a slice of that. Before they cache the simulation, let's change it, apply some force here. Pop force. Let's change the force like 0.8 and amplitude to 2. We need to change this to this activate attribute to 1 and create the simulation. Very cool. The simulation is working by simulating just the activated piece, and you can see here almost real time in the viewport without the slowing. Right now you need to, because this is a low geometry version of the head, we need to apply each low res geometry to their original mesh. For that, we need just to file cache the information before this remesh and change here the name to cache remesh original mesh. Just disable time dependent cache. Change the base name to parent node name, and in the advanced tab disable harden based on save and just cache the file. Okay, this is the high-res version of the geometry. We need to deform this geometry by this piece here. We need to create a point deformer using a time shift of the first frame. Create a time shift and delete here channels to frame just to 1. Connect here the time shift to the second input of the point deformer, and the third input it should be the animated cache. You can see a horrible geometry information because you need to use the piece attribute name just to deform each fragment. Should be deforming each high resolution fragment, not the entire geometry. Like this. Let's create a cache, checkpoint, F, original mesh simulate. This is the start of the chapter 2. Right now we just have the peeling information, peeling simulation here. We don't have the disintegration yet. For disintegrating piece, we need to shrink each fragment, like remove the points of the border here. Each frame you need to remove some points from the border. For that, you can use a solver. Let's create this setup. Let's organize this node here. Here, we create an attribute promote. Let's promote the active piece from point to primitive. Promotion method should be average. Okay. Here's the active piece. Let's see the activate piece. Change to black. And create another color. Color, activate piece. Change this to primitive, change it to red. In the group should be expression here. Activated pieces. It's like a VFX expression inside the parameter here. Activate piece equals 1. Remove this I. It's working. All the activate pieces are red right now. We can change the color like white, just to see more information. We need to promote the color. Primitive to point and use the average default method. Let's remove some attributes that I don't need here. Delete everything except CD. Here we need to create a solver. This solver here is just like a simulation in SOP context. Connect here. Let's change the name to solver frames since activation. In this solver here, we are going to calculate how each fragment piece was activated and calculate how many frames each fragment are floating. For that, we need to create a VFX expression. Let's create an attribute wrangle here. Change the name to VFX start frame. Change the color to purple. And create the expression here in points. At frames since activation equals 0. Let's go inside the solver and create some setup here. First of all, let's create a cache after the solver before working inside the solver. Let's change this name to cache. Frames activated 0, 1. Change this to time dependent, okay. Base name, parent node name, harden base, initialize simulation ops. Let's go inside the solver and create the setup here to calculate which each frame starts each piece. We need to create a VFX node here. Change this node to purple, rename this to VFX, frames, since activation, connect the prev frame to the first input of the node, connect the out here, and connect the input in the first input here. And you write some script here, the VFX code. Vector color equals point. We need to get the information of the color in the input 1. The color red, actually, let's change this to red color instead of white. Much better. Let's go back inside solver. Vector color equals point 1. We need to grab the seed information for each point. Add ptnum. Let's check the color. If color dot red greater than 0, set the attributes. At frames since activation plus equals 1. We need to calculate the increment the frames since activation variable by 1 each frame. Let's create another VFX here, attribute wrangle, rename this to VFX, copy P and CD. We need to copy the position from the balance simulation to this solver node. Let's change this to the purple color and copy some information here. At P, we need to copy the position equals point 1, grab the position for each point. At CD equals point 1, grab the color for each point. Just that. And you can cache the simulation. This simulation will not be different from the simulation already done. We just need one information here. We just need to create this variable and activate this variable for each activate piece and calculate the frame number. Just that. This solver here doesn't change the geometry at all, just the attributes for the frame simulation. This solver here this cache here is super fast, less than 10 seconds, just to grab this activated variable here. Just that we need. Now let's copy this attribute. Attribute transfer. We need to transfer for original geometry this attribute here. Frame since activation. Just that. We just to grab this information here. Let's delete some attributes that we don't need. Let's delete the rest and delete the just that. Let's delete some groups here to cache the geometry. Avoid the waste of the disk space. Let's delete all the groups we don't need and create another cache here. Right now this cache should be named like cache point deformed original. Change the parent and node name and disable harden base and activate initialize simulation ops. Let's create a color node here, just to set white color in the points. Right now, we just need to shrink each piece, each activate piece, like remove some points from the border. For this, we just need to create another solver and make the setup here inside here to remove some boundary, the edge points. Let's create a setup here. Let's create a solver. Connect here. First, we need to create another point angle. Color to purple and rename to Vex. ID and valid PT attributes, and create some expression here, some Vex expression. We need to initialize just two attributes: ID, which grabs the PT num value, at valid PT equals 1. In the solver, after the solver, let's create another cache. Let's change to cache disintegrate. This node here, you will disintegrate the geometry. This solver disintegrate geometry. Disintegrate geo. Change some attributes here, the file cache, base name, harden base, initialize simulation ops. Let's go inside the solver disintegration. And they created another setup here. First, we need to create a Vex. Rename this to Vex get P. Connect here, change it to purple, and connect the first input, the input 1 to the second input of this Vex. The code should be like this. Int ID equals ID to point 1 EID. EAT ID. We need to grab the ID information, the PT num information from this ID, and set the position here. 1 grab position for each ID, just that, and create another pointer angle and change the name key here to remove borders. This Vex node should be remove the borders, like remove some vertex of each border of each fragment piece. Change the color here to purple and connect the input 1 to the second input from for the Vex node. This should be a more complex node of Vex script. Let's write line by line and explain. First, we need to create some variables and parameters. Int PT num, ID to point, 0, EAT ID. Int count equals neighbor count. We need to grab the how many vertex neighbors, how many point neighbors for each point. Let's create a variable here, float chance, if the points have chance to be removed or not in the actual frame. take some space here. Let's correct the script here. Add frame, another variable, int frames since activation equals. Let's grab the frame activation attribute from the second input here. Frames since activation. And creation a condition here. If, copy this variable here, if frame since activation greater than another attribute here, another parameter, call it the start anim. Create another if here, if count. If the vertex count around each point neighbors should be greater than another value here that you will define. This parameter count and chance less than chance defined by parameter. Mean chance should be remove the points. You see the variables and set the variable values should be clicked here. Create spare parameters. Anim start should be 20. Count should be 3. And mean chance should be 0.6. Before creating the cache, I forgot something. We need to clean the geometry. And make the cache and see if that's working. Right now you can see that this integration is too fast and we have a problem in the first frame. I think the cleanup node is removing a lot of points before even the start of the simulation. Let's adjust that. Let's fix here 0001 and create a cache again. Let's see if the simulations are working. Let's compare that information before the disintegration. Yes, it's working. Here the original all the original piece without the shrink by edges. In here is the piece around almost shrinked. That's working. Before going to the next step, we need to copy this information here to create the particle simulation. For this, we need to create a simple setup here. We need just create a color, a basic color black. Create a vex node here, point, just to copy the color for each point. Let's call it vex, copy color. We need to copy the original color here. To this geometry. But first we need to create another color. Change the red. You just need to create this red color to each point. Just that. Sorry. We need to color this purple and just copy the color. Int ID equals ID to point from one input, second input for each ptnam. If ID Gradient equals then 0. Set the color to red. Just that. Let's calculate the trail. We need the velocity here to create a particle simulation for the disintegration. Create a trail, compute velocity, match by attribute ID, and evaluate within frame range. Let's delete some attribute here. We need to remove the attribute name. Original name should be removed because we need to restore this attribute like a name. We need to remove these piece names and restore the old name to original attribute name. For that, we need to delete the name. In primitive, remove name. And rename the old name attribute to name. In primitive, old name to name. Now restore the original name of this geometry. And let's create the final cache here. Before the render, let's rename this to cache. Disintegrate final. Change the base name, disable hard base on save, and initialize simulation ops. And create a checkpoint here. Alt arc disintegrate. Change this to black. And create a cache. Before that, let's color this to white. And see if the simulation is working. The simulation is working for the clipped geometry. Right now you just need to disable the preview and apply it to the whole geometry, the simulation here. Let's do that. We know we need to recreate this cache. Let's change the color here to make it more visible. This cache we need to make, this cache. We need to make this cache in the order. This cache here, this cache here, this cache. Let's switch the previsualization and make the caches again. Actually, before this cache, we forgot some information here. We need just to remove these black points here. Just split because they are disintegrated and I forgot to disintegrate the black piece. Add cd.r greater than 0. Points inverse selection. Now that's correct. We need to remove the black piece and make this cache again. That's the simulation of the geometry. The simulation is ready for the next step. Now we have the simulation working fine, just fine. We need to emit some particles from the geometry. For do that, we just need to go here, create a node, geometry node, and name this to arc particles. Grab this node here, Ctrl C, go inside the arc particles. Let's disable this node, visibility, create object merge, and paste the path here. We need to make some preparation here in the geometry. First, we need to apply another velocity. Compute velocity, match by attribute, evaluate with framing range. We need to decide where to emit the particle. For that, we need to create a VOP network, point VOP, connect the first input. Let's change the color here to red and the name VOP emission. I think we are going to use the velocity to apply the emission locations. For that, we need to dive inside the VOP. Let's make some simple network here. Calculate the length of the velocity. Let's fit range the velocity. Create the spare parameters here. Input parameters. And apply some ramp parameter. And see the color here. Our minimum value should be 0.25. And maximum velocity like half, almost half. And change the ramp here to black, white, and black again. Just the intermediate simulation for each fragment. And using VEX, we should be remove all the black points. Let's remove these points by luminance. Float, luminance, lum equals luminance by color. If lum less than threshold, we're going to create here. Threshold. And by that, we will remove the point by picking none. The threshold here should be 0.1. And just keep the white points. That's the point that should be creating the particles here. Let's change this to purple. Let's make all the colors white. Clean up the geometry that we don't need. And create a file cache here just for emitter. Cache, emitter, particles. Let's delete some attribute here to avoid conflict in the particle simulation. We are going to delete ID and make the cache. Change the base name and hardware base on save and initialize simulation ops. Let's save. Seed our cache. That's it. That's the points we're going to emit the particles. Let's create a checkpoint here. Ref emitter. And let's create the particle simulation. Pop network. Rename this to particle sim. Let's go inside this node. But first, let's create a setup to save the cache here. File cache. Cache particles. DOP import fields. Connect here. We need to reference the pop object here in the DOP import. We just need Ctrl+C, Ctrl+V here, and put the DOP node here. Choose the particles, and let's go inside this node. Let's change the network here. First, we need to change the source in first input. Source first context, okay. Scatter on surface, perfect. In the birth, we need to increase this value here. Like 50, 100,000 particles. Decrease the life expectancy to 1. And the variation, a little bit variation in the life expectancy. Let's put a pop force to make some variation. Like 0.7 and 1 of amplitude. We can remove this merge here. We need some drag, pop drag. Let's reduce your air resistance to 0.1 and make some pop color too to generate the alphas by age. We don't need to update color, we just need to update alpha. Alphas should be used to vex expression like fade with age, okay? And you need to collide with the ground. Merge, ground, simulation, okay? We don't need the gravity here. Let's change the cache here, parent node, database on save, initialize server simulation ops. Let's save the simulation. The simulation is working. Let's see with the cache, jump to cache here. The particles is working and the simulation is working. Now let's adjust the P scale for the rendering. First, let's delete some attributes we don't need here. Delete all the attributes and keep the velocity. Keep the alpha and keep the ID. Let's delete all the groups we don't need. Adjust the P scale using FX. Color to purple. Let's create some variation here in the P scale. Float mean scale equals some parameters mean scale. Float max scale equals some another value parameters max scale. At P scale equals fit the sum random value by ID. Min P scale max scale. Fit 01 and let's change some parameter here like 0.001 05 0.001 and create a checkpoint here. Particles. Let's change the pre-visualization of the particles to pixels. Let's create a preview here. That's the final simulation. Right now we're just going to render this in Redshift. Now let's start to render the simulation. Let's create a loop network. Rename to look dev. Arc disintegrate. Let's go inside this node and create our Solaris hierarchy here. First, we need to import the arc geometry. Select here, arc disintegrate, alt arc disintegrate, and change it here to copy layer. Create another SOP import and change the name to particles. Load the reference here to particles, alt particles, and change the sublayer style to cop SOP. Let's merge. Let's set up the camera. Let's create a material library and assign material, and go inside the material library and start to create the shaders. Redshift material. Create some materials here. Let's rename this to Redshift head. Copy material. Redshift eyes. Copy material again. Redshift teeth. Another copy. Redshift rings. The ring should be Algeria here. Create another shader. Ground. Yeah, we don't need the ground. Particles. You can change the visual of the shaders later. Let's apply some lighting here. Create an air light fill, and place in the front of the arc. Check if the side is good, okay. Create another air light here. You call it the him. And put in the back of the head. Let's check if the size okay. Perfect. And create a Redshift node here. Enhance arc. Disintegrate. Let's change the resolution here to HDTV. Change the quality to custom. Advance the mode. Disable. Increase the threshold just for test renders. Here we can create a dome light with a ADR, simple ADR, dome light. I grab a simple ADR here. And let's check the render. It's too white, we need to adjust the shaders and apply to the shaders to the objects. First, let the outfill materials here and apply each shader for each object. We need these 5 materials For each piece of the geometry, let's put here eyes, arc head, arc rings, arc teeth, and the particles. The material should be applied eyes, head, particles here, rings, and teeth. First, I think I will disable this R light here. Just see the dome light. Let's go inside the material library, check the first frame, and change the eyes to black. Let's change the eye to black and enable the roughness. Let's disable metalness and increase the roughness here. It's working. Right now you can change the head color, like a dark color. Increase the roughness, like 0.7. Increase a little bit of the brightness. Okay. Let's change the teeth. Decrease the roughness. Okay. Let's change the rings like a chrome. Increase the roughness a little bit and decrease the color, the lighting. Like this. Here, it's working nicely. Let's change the area light here. Put some temperature color. First, disable the dome light and just let the area light fill. Enable color temperature. Like warm color. The ring light should be a cold color. Let's increase the exposure. Like 3. In the area light fill should be increase the exposure too. Like 1. And enable the dome light. Maybe decrease a little bit of the dome light. Okay, now let's apply the shaders to the particles. Let's move here. Redshift has a problem. I cannot see the particles here in the viewport. I need to render and see what is happening with the particles. For this, let's activate output in plane monitor. And first we need to apply the material to the particles. Let's change the color here, like a brownish color. And decrease the roughness. Actually, let's disable the roughness. And decrease a little bit the opacity. And activate the motion blur here in the particles and the arc. Create a render geometry settings, and in Redshift change here to set your create velocity blur. And let's see the render. Let's disable the backdrop of the dome light. In dome light, in backplate, enable the backplate here. And let's render again. That's cool. Let's see the start of the animation. Like this. Like this frame. Let's disable the viewport and seeing the gameplay. Cool. It's working perfectly. That's it, guys. This is the final render. It should be a complete disintegrating the arc with particles and geometry. Thank you, guys. See you next video.